Hi, my name is Curran Gahan, and I'm a fifth-year graduate student in Professor David Lynn's group. In the Lynn Lab, we specialize in the synthesis, characterization, and application of soft materials, including polymers, liquid crystals, surfactants, and lipids. My research specifically relates to studying the interactions of bacterially produced surfactants with lipid membranes. Other research in our lab uses the tools of layer-by-layer assembly to create thin polymer films on surfaces. As I take you through the lab today, I'm going to show you each of the three steps in the synthesis, characterization, and application of the materials that we make in our lab. Now, one of the things I like the most about working in the Lynn Lab is actually our office spaces. As you can see, we have a large office space where all of the Lynn group members can sit together. This is very advantageous in doing research because you can talk to all of your additional lab mates and talk to them about problems that you're having in your research or ways to interpret your data. And it's a really nice way that we can all collaborate on all of the different projects happening in the Lynn Lab.
The first step in any project is the synthesis and procurement of our starting materials. This often involves some degree of organic synthesis and includes monomer as well as polymer synthesis, which in turn can be used to fabricate films, gels, or other materials for our projects. In this clip, you can see our main synthesis hood, which includes all the common tools for organic reactions, such as oil baths, vacuum pumps, and of course, Schlenk lines for controlling the reaction environment. We also have all the necessary separation equipment for our reactions, such as a rotovap, a lyophilizer for removing aqueous solutions, and a vacuum oven for removing residual solvents from our reaction products.
After we've either synthesized or purchased our starting materials, we then have to turn those starting materials into our useful and functional materials. One of the main platforms that we use for developing functional materials in our lab is layer-by-layer assembly. And what this is that when you put two mutually reactive or interactive polymers and we dip a substrate subsequently into alternating solutions of these polymers. So for example here, when we have solutions of polyelectrolytes, polycations and polyanions that will absorb and interact with each other on the surface of a glass slide, we can subsequently dip them into the solution of polycation, a rinse solution, then the solution of the polyanion, and a rinse solution. Then we can repeat this process over and over again. Now this process is relatively time consuming, and so one of the ways we've been able to automate the process and speed it up is by using the dipping robot that you see here. So we can attach our substrate to the robot, and we can automate or program the robot to dip this into subsequent solutions of various polycations or anions, as you see here. Now this robot's really nice for aqueous solutions as they're not volatile enough to, over the course of 5-6 hours, dry up. And this presents a challenge when we're using organic solvents, especially volatile organic solvents like acetone that we use in our layer-by-layer assembly process. And so we can either dip them by hand, which we do often and is time consuming, or in our lab we're coming up with new and novel ways of creating layer-by-layer films.
As discussed previously, when using volatile organic solvents, the robot dipping method cannot be used, and usually we have to use the hand dipping method, which again can be quite time consuming. Therefore, our lab has been recently utilizing spray techniques for the deposition of layer-by-layer films in organic solvents. In this technique, the two mutually reactive polymers are sprayed and then rinsed sequentially just like before, and can be repeated as many times as needed to obtain the desired thickness. As you can see, this is a fully automated process, which allows better efficiency in all our fabrication techniques.
Now that I've shown you how we use layer-by-layer assembly to form robust films on a surface, I want to show you two of the main applications that we target using these films. The first of which are non-wetting surfaces, and the second of which are slippery surfaces. And I have an example here to show you each of those. So, for example, we have just a plain glass slide here. When water interacts with this glass slide, it wets the surface, and as you can see, it sticks to the surface in many places. While it does roll off the surface, it does stick and fouls the surface in a lot of different spots. But if we go, for example, to a non-wetting surface, also known as a superhydrophobic surface, when water comes in contact with the surface of the slide, it immediately rolls off, bounces off actually in many cases. And so this is why it's called not wetting, because it doesn't wet the surface, it's hydrophobic, and immediately repels the water droplet off of the surface of the glass slide. Now if we take one of these superhydrophobic surfaces and we infuse them with a layer of oil, we get what is known as a slip, or a slippery liquid infused porous surface. And what happens is that that oil that's now infused into this film acts as a lubricating layer between the glass slide and the water droplets. And so now that we have a few of the water droplets on our slide, as you can see when we tilt it, these water droplets freely move across the surface of the glass slide. And when we tilt it too much, they run off the surface and don't stick to the surface. And so we often use slips for non-fouling applications, when you don't want anything in the water to stick to your underlying substrate. One of the main ways that we're able to characterize our materials, like thin films, polymer capsules, and lipid bilayers, is with optical microscopy. Our microscope allows us to observe phenomena on the micron scale, both by bright field and epifluorescent microscopy. In the following images, you'll see some example data that we collected using our microscope, looking at LC sensors, supported lipid bilayer films, and polymer capsules. More microscopy data can be found in the publications from our group.
In addition to the equipment found in our own laboratory, there are many shared use facilities that can be found around campus containing a multitude of specialized equipment that graduate students can be trained to use. One of these facilities that the Lynn Group commonly uses is the Soft Materials Characterization Laboratory, or the SMCL. This facility includes equipment that can be used to characterize polymers and polymer solutions, or suspensions of nanoparticles or surfactants. Some of the common equipment that we use in the SMCL, as well as in other facilities, are shown here in this non-comprehensive list.
Finally, I wanted to show you our cell culture room. This is the room in which we culture mammalian cells. Many of the applications that we target in the Lynn Group are in the space of biotechnology, and therefore we want to put them in cultures with either bacterial, yeast, or mammalian cells. While we do this mammalian cell culture ourselves, if we want to include our materials with bacterial cultures, we often collaborate with Professor Helen Blackwell's group over in chemistry. And if we want to introduce our materials to yeast cells, we collaborate with Professor Sean Palachek here in the Department of Chemical and Biological Engineering. We also have many other collaborations around campus. We collaborate with the Veterinary Medicine Department, as well as the School of Medicine, for many of our animal wound models. And additionally, we collaborate with many other groups here in the Department of Chemical and Biological Engineering that have expertise in other areas. This is one of the reasons why I chose to come to the University of Wisconsin-Madison, and why I'm really happy with my choice even to this day. And that's because we're a very collaborative community and environment here at the University of Wisconsin. Collaboration is never discouraged and is always encouraged by our professors, who ask us to work together and leverage each other's specialties so we can make our scientific projects as impactful as possible.
Hi there, and thanks for watching our video. If you have any questions at all regarding our group and our research, please feel free to contact any of us by going to our group website, shown here, or by directly emailing our principal investigator, Professor Dave Lynn.